So on Friday, we looked at finding the equation of chord. That's one of the key features in parametrics that we look at. Tangents and normals are another key lines, or lines is plural, I suppose I should say. Now there's two different approaches. We could do it using parametrics, which is what we'll look at today, or we could do it looking at Cartesian coordinates, which we'll look at tomorrow. So let's do it using parametrics. So first of all, finding the equation of a tangent. So there's good old parabola, but x squared equals 4ay. I'll pick a point P, I'll give it the form 2ap, ap squared. So P is the parameter of our point. And we're going to find the equation of a tangent. This is no different to what we were doing last term. I want to find the equation of a tangent. We need two things, a tangent's a line, we need a point, we need a slope. I've got a point. Oh, how do I find the slope? Slope formula. I need 2 points. I haven't got 2 points. Damn. Calculus. Excellent. To the rescue. So let's differentiate. I'll rearrange it so y is the subject. That'll make differentiation a bit easier. So differentiate x squared, we of course get 2x, but the 2 cancels with the 4, so x over 2a. But remember, that's just the formula that allows us to find the slope. Okay, we could have done it implicitly. If I did do it implicitly, I'd do it this way. X squared equals 4ay. So differentiate x squared, I get 2x. Differentiate 4ay. Sorry, can't do it with respect to x, but I can do it with respect to y. So I get 4a, but I have to multiply it by dy dx. Rearranging, again, I get x on 2a. Either way it works. I probably would go with the first way myself. Okay, we want to know at the point x equals 2ap. 2ap dy dx equals p. That in itself is quite a nice little result. Because what it's saying is the slope of a tangent at any particular point is in fact equal to the parameter at that point. So if that's where p was equal to 1, the slope would be 1. If that's where p equals 2, the slope would be 2, and so on. Okay. Now, of course, another way I could have done it, I could have left it as x equals 2a, well, t or p or whatever, but x equals 2at, and I'll differentiate that with respect to t, and I get 2a. Y is at squared, I'll differentiate that with respect to t, and I'll get 2at. But remember our chain rule, rates of change, implicit differentiation, call it whatever you like. Dy dx equals dy to t times the t dx. So I get, again, the parameter, t. And we're looking at the point where the parameter is p, so the slope is p. Again, I'd probably go with the first way. But there are all different ways we could come up with that same result. Okay, slope of the tangent is p. So y minus y1 is equal to slope outside of x minus x1. Let's expand that out. Y minus ap squared is px minus 2ap squared. I get y is equal to px minus ap squared. So there's a general equation for a tangent, and all I've got to do is substitute in the parameter, and I can find the actual equation. Okay. Tangents from an external point. Well, what happens is if I don't know the point of intersection. So there's some external point, I'll call it 3, 2. From any external point, I should be able to draw 2 tangents. Same as with the circle. Remember when we were doing with circles, you could have an external point and you could draw 2 tangents to the circle. Same with the parabola. So there'd be one going down there, there'd be another that would be going up quite steep. Well, let's say the point of contact, I don't know what it is, so I'm going to give it its parametrics. Notice this one has a focal length of 1. So I haven't called it 4ay, I've just called it 4y. So hence my point's not 2ap, it's just 2p, and ap squared is just p squared. And there's the other tangent. So it doesn't matter where I put that external point, I could always get 2 tangents. But q, I'm going to give it a random point, 2q squared. Remember, I don't know what those coordinates are. Okay, differentiate y equals x squared on 4. Dy dx is x on 2. When x equals 2p, dy dx equals p. Same as I just did, basically, y minus p squared, except I haven't got an a this time. Y minus, right, so there's my equation of the tangent. But again, I don't know what 2p is and p squared. But I do know that this tangent goes through the point 3, 2. So I could substitute in the external point, p squared minus 3p plus 2 equals 0. And I can work out the two parameters. And so now I know where it touches the parabola. One would be at the parameter where p is 1, and the other would be when the parameter is p is 2. So now I can go back to my equation of a tangent. Well, because I know what the parameters are, well, when p equals 1, I'll get y equals x minus 1. And when p equals 2, I'll get y equals 2x minus 4. And there's my two equations. So that's a way we can find the equation of the tangent even when the point is not on the parabola itself. It could be some external point. But if it is from an external point, we'll usually end up with two possibilities for the tangent. Find the point of intersection of two tangents. Okay, once again, there's good old smiley parabola, x squared equals 4ay. There's one random point. I'll call it 2ap, ap squared. Amazing how that point keeps coming up. There's a tangent. Now, I'm not going to do it again. I've already done it twice. So the first thing I'd do would be go and find the equation of our tangent. If you're doing it in a test, only ever derive it once if you have to. Okay? Because if I'm finding the point of intersection of two tangents, there's my other one, I'm not going to derive the equation of this tangent. That's the whole benefit of using parametrics. So once I know the general equation, y is px minus ap squared when the parameter is p, well then I know the equation at q, because the only difference is the parameter. The parameter here is q, so therefore the tangent at q must be y equals qx minus aq squared. I'm just changing the parameter. We want to find the point of intersection of those two lines, so we'll solve them simultaneously. I'll creatively call that point of intersection t. T for tangent. Solve simultaneously. Okay, well those y's will eliminate nicely. So I get p minus qx is a, p squared minus q squared. But of course p squared minus q squared, difference of two squares. And that'll cancel the p minus q's. Now, can I do that? Remember, we can only cancel algebra if we're sure that it can't equal 0. Is it possible for p minus q to equal 0? And the answer is no. I did see a few people shaking their heads there, but weren't game enough to go, no! Okay? Because if p minus q is equal to 0, p would equal q. So it'd be the same point. So we wouldn't have a point of intersection of two tangents because it's the same point. So it is okay to divide by the p minus q. So the x value is a outside of p plus q. Substitute back in, and we end up getting for y, APQ. So there's our point. The x value is a, and we add the parameters together, and the y value is a, multiply the two parameters together. Normal then. Let's find the general equation for the normal. Remember, a normal is a line that is perpendicular to the tangent. So go off at that sort of angle, I guess. Well, okay, again, I'm not going to do it again. We've done it a couple of times already. But I could show the slope of the tangent was p. But we want to find the slope of the normal. So therefore, the slope I want is minus 1 on p. Point slope formula, y minus ap squared is minus 1 on p, x minus 2ap. This one I think looks a bit ugly. That's just my opinion though. X plus py is ap cubed plus 2ap. So there's an equation of a normal. Let's find where they intersect if we've got a couple of them. So there's my normal at p. And so again, we would go and derive the equation of the normal. There's our normal at q, but once I know the equation of the normal at p, I can say, well, the normal at q then, I'm just changing the parameter. It'll be x plus qy is equal to aq cubed minus 2aq. Solve these simultaneously. They intersect at n. This time it's the x values that'll cancel nicely. So let's do a subtraction. P minus qy is equal to a p cubed minus q cubed. Difference of two cubes. That will have a factor of p minus q as well. So let's expand that. Oh, sorry, factorise that, I should say. P minus Q, P squared plus PQ plus Q squared. Divide everything by P minus Q. I end up with Y equals, well, there's a common factor of A, P squared plus PQ plus Q squared for the first term there. The second term, we've cancelled the P minus Q. We've factorised the A. So all I'm left with there is plus 2. So there's our lovely Y coordinate. This is probably a good reason why we don't bother memorising these. So we derive them each time because, wow. Now I've got to substitute back in to get the X value. X plus APY, so there's our Y, and there's our X value, minus APQ times P plus Q. Wow, what a mouthful. The X value is minus APQ P plus Q, and the Y value, A, P squared plus PQ plus Q squared plus 2. I'm sure you would have guessed that anyway. Right there. Alrighty, so 9F.